Okay, so covalents are probably the easiest because all you have to do is say how many of each element using mono, di, tri, tetra, penta, hexa, hepta, oct, non, and dec. You're never going to see those probably, but there they are. And then you change the ending to "ide" on the second one. That's a very normal thing to change that ending to "ide," both for ionics and covalents. And the only weird thing is we don't say mono if there's one of the first one. So carbon monoxide has one carbon and one oxygen. We don't say monocarbon monoxide. We just say carbon monoxide. Okay? So if there's one of the first one, you leave off the mono. Okay, so let's do all the covalents, and then we'll come back and talk about the different types of ionics because those are the trickier ones. All right, so all of these, there's formula to name and name to formula. So in this case, iodine, so we don't say mono, and then there's 5 fluorines, so we're going to say pentafluoride. Again, the ending changes to "ide." The next one here, carbon tetrachloride. So 1 carbon, 4 chlorines. Tetra is 4. Dichlorine, so 2 chlorines, pentoxide. Sometimes you'll see this as pentoxide, and sometimes you'll see it as pentaoxide. It's just, I don't know if you call it preference, but I've seen it both ways. Sometimes we drop the A in order to avoid like a double vowel, whatever. Neither one is really right or wrong. So 5 oxygens and 2 chlorines, so Cl2O5. The last one there, di for 2, phosphorus. So the ending is only for the last one. So we leave it diphosphorus, and then oxygen goes to oxide. Diphosphorus pentoxide. Okay, second column up here, tetraphosphorus, so 4 phosphorus. Don't ask me why there's an X there, that's a typo. Tetraphosphorus trioxide, so 3 oxygens. And then the last one, sulfur, we don't say mono. Tetrafluoride. Okay, so I would say covalents are the easiest because there's just a lot less ways to get it wrong. So if you ever have a list like this where you have lots, just go ahead and do the covalents first, get them out of the way. Okay. All right, for ionics, so we've done covalents. This says molecular. You don't care why at this point, but it means covalent, okay? So non-metals only. So we've done those. Now we need to look at ionics. So 2 types, remember, type 1 is when they can only form one type of ion. Type 2 is when they can form multiple ions. So I did this multiple times in the video because I know you guys all watched it. Where did it go? Oh, because it wasn't on this one. I highlighted it on the 9 a.m. class one. There we go. Okay, in the video, I showed you this chart where I highlighted the type 1s in yellow. So it's mostly the main group elements, and it's based on their column. So if they're in the first column, it's +1. Second column, +2. Third column, +3. And then there's these 3 in the transition metals that are also type 1. So silver is +1, zinc is +2, and scandium is +3. You just have to memorize those. Okay? The purple ones, you don't have to know what their charges are. You just have to know that they have multiple possible charges. So the way we indicate the charge is with Roman numerals. So if you're given the name and you see that like iron 3 oxide, they're telling you the iron was a 3+ charge. if you're the one doing the naming, so you see FeO, you're the one that has to say what the charge on the iron was. In that case, iron 2 oxide. Okay, so that's the case for the other transition metals and tin and lead, Sn and Pb. Okay, so if you're writing a compound with tin or lead or one of the transition metals other than those, then you need to make sure to include the Roman numerals. That's kind of the key difference. That should be included in there. Or in the case of multiple choice exam, you can immediately rule out the ones that don't have Roman numerals because you're going to know that that's not the correct answer. Okay, so switching back to, there we go. No. Okay, there we go. All right, so what I'm going to do now is I'm going to go through, and the ones that say ionic, I'm going to label them as 1 or 2. The caveat, and I refuse to call this type 3 anymore, is polyatomic ions. So polyatomic ions are those, basically they're a molecule that lost or gained electrons. So they're like a covalently bound molecule that became an ion by either losing or gaining electrons, and now they behave usually like a nonmetal. So in most instances, the list is here. In every single instance except for one that you guys will see, they're negatively charged. So the only positively charged one is ammonium. So if they're negatively charged, what's happening is they're substituting in for the nonmetal. So like if we had sodium chloride, a similar compound with a polyatomic ion would be sodium something. So maybe sodium acetate, NaC2H3O2. It can be really helpful, even if you only have one of them, to write parentheses around it just to remind yourself that's a polyatomic ion. So it's like that's the negatively charged thing, the sodium is the positively charged thing. So every one of these except for ammonium is going to take the place of the nonmetal in an ionic compound. The naming component is actually easier because you don't have to change the names at all. It's just whatever it is. If it's sodium and that formula, it's acetate, sodium acetate. That's all we would say for that name. Lots of professors, in fact, I think I'm the only one that I know of that doesn't require you to memorize them completely. Most professors will just say, okay, you have to know all these names and formulas. So they'll give you something, like Na3PO4 and assume that you're going to know to name that sodium phosphate and not confuse it with phosphite or phosphide or something like that, okay? I feel like there's only so much room in your brain at a time. I know it's not true, but in your short-term memory, that's true. So I don't want you to have to keep absolutely every little detail that maybe I could give you a little bit of a hint with. So on the exam equation sheet, you'll see this list just without the names. So when you look, it's easier when you're going from name to formula. So if I said sodium nitrite, you would be like, okay, I know sodium's Na and nitrite. What is nitrite? So then you go to your exam equation sheet and you look through the list. Again, it's just the formulas. And you're like, okay, I know it's not any of those. It was a nitrogen compound. Okay. All right. So there's two possibilities here. Which one was nitrate and which one was nitrite? So that one you have to remember. But you won't mix up the fact that it's 3 oxygens versus 4, or that the charge is -1 versus -3. That's where the exam equation sheet list can be really useful. Okay? So do you not have a chair? That's so sad. Here you go. How do we have a room but there's not enough chairs? Okay. All right. So back to the examples. There's still type 1 and type 2 based on does the charge change. Ammonium NH4 plus is the one rare one that's a positive charge, and that only has a positive 1 charge. It doesn't change. So it would be considered a type 1. Okay? All right, so I'm going to go ahead and label these. This is a 1. Chromium is a transition metal, so that's a 2. Lithium is in column 1, so that's a 1. Tin is one of those that has multiple charges, so that's a type 2. Calcium, that's a type 1, that's a main group element. Ammonium, we know the charge, so that's type 1. Aluminum, type 1, it's in column 3. Calcium's type 1 as well. Okay, so we only have 2 type 2s in there, the chromium and the tin. So maybe we should start with those because then the others will seem easy. Do I believe that? No, I don't really believe that. Let's do type 1s. So again, type 2s are the ones where we're going to have to indicate the charge. So let's do the easier ones first, the type 1. And if you have the formula, you just write down the name of the 2 things. You change the ending to "ide." NH4 is called ammonium. So I write down ammonium. Phosphorus gets changed to phosphide. Ammonium phosphide. Okay, I'm going to skip down to lithium carbonate. So now we're going the opposite direction. We're going from name to formula. So anytime you have that, you write down the first part with its charge. You write down the second part with its charge. This is where that list is going to become really useful. Let me just show you on the exam equation sheet what it looks like. Okay, it looks like this, polyatomic ions. So when you're looking at this and you're like, lithium carbonate, you're like, I know it's carbon something. Okay, it's not chlorine, so it's not these guys. It's not chromium. Okay, there's 2 with carbons, and hopefully you remember that it's just the carbon-oxygen one. So now you don't have to perfectly remember that it's CO3 2-. You can use this list to get you close enough, and then you use the list to make sure you get it right. The charge in particular is hard for people to remember. Like, is it a 2- or was it a -4? I don't know. Okay, so then we go back over here, and where did I have that? Oh, I already did that. Okay, so lithium and carbonate, and now we need to cross the charges so that we get the formula where everything balances out to 0. I can see pretty easily that this needs 2 lithiums for every 1 carbonate, right? Because it's a -2, so I need 2 positive lithiums. But you can also just do it with the numbers up here, go down there. Okay? When you have a polyatomic ion, like I said, it's a good idea to put parentheses around it. In this instance, it's not going to matter, but we'll see in a second examples where if you had 2 carbonates, you have to indicate that with a 2 subscript, and you don't want it to look like you're writing 32 oxygens, so you put the parentheses to say 2 of these things in the parentheses. All right, so I'm going to erase the charges on mine and bring the number down. So it's Li2CO3. Okay, next one, calcium phosphate. Again, name to formula. So I'm going to do Ca2 plus phosphate. Phosphide, this is where you're going to hate me or hate chemistry. Phosphide, ide, would be an individual element. So the ide is always an element. If it's 8 or ite, that's indicating that it's a polyatomic ion. Okay, so phosphide, phosphate, phosphite, all different things. You love me right now, I know it. All right, PO4 3-, that's phosphate. So we're going to cross the charges, but because it's a polyatomic ion, I better put parentheses around there, okay? So I'm going to cross the 2 down to phosphate and the 3 down to calcium. So the formula of calcium phosphate is Ca3PO4 2. Now, on an exam, it's multiple choice. Phew. So let's say I have this question on an exam, maybe I've got, this is the correct answer. Maybe I also have like Ca3P2. Okay, that would be a nice potential incorrect one that you might confuse. That's actually calcium phosphide. Or maybe I have Ca2PO4 or maybe I just have CaPO4. Okay, so these are some potentially incorrect answers. But do you see it's not as bad as when you're doing free response? Because if you're doing free response, you have to just pull phosphate out of the air and make sure you have the charges and make sure you do the charge crossing. When you're looking at a list of potentials with multiple choice, use that to your advantage. Like rule out what you know. Like, okay, immediately, right, Ide is the one that's just an element, so it can't be that one. Then you think about, okay, what is the charge on these? So what would the formula then be? So like you can work at it from the question to the answer. You can also use the answers to kind of work backwards and, you know, figure out which one's correct. Okay, ammonium sulfide. Ammonium is one of those few that is positive, the only one that you'll see that's positive. So it takes the place of the metal. So NH4 plus. Sulfide, ide means it's the element. So it's just sulfur, which has a 2- charge. Sulfate is SO4. Sulfite is SO3. I'm trying to think if there's other. I can't think of another one. Oh, HS is hydrogen sulfide. That's hydrogen sulfide, so not just sulfide. Okay, so then I cross the charges. Again, polyatomic ion, so I'm going to put parentheses around it. And I'm going to bring that 2 down. So I can erase easily on your paper. I would just rewrite it. So the 2 comes down, the 1 comes down, so it's NH4 2S. So it's really important that I indicate 2 of the ammoniums, because what that means is that I've got 1 S2 minus, 1 NH4 plus, and a second NH4 plus. Okay, so they are individual little units, just like a molecule, except for they lost an electron along the way. And so it's 1 of these, 2 of these. So when we say a 2 subscript here, the parentheses are telling us it's a little unit, but I've got 2 of them. Okay, last 2. Aluminum phosphate. So aluminum is a 3+ because it's in the 3rd column. Phosphate. The trick with the 8s and the ites, the 8 is always more oxygens and the ites always less. So if you had to remember exactly the correct number, that would be hard. If you look at the thing, you always know the one with more oxygens is the 8. So this is 8 and this is ite. This is, do you not have to know phosphite? I guess you don't. There is a PO3 3-, which is phosphite. This is phosphate. Sulfate and sulfite. Okay, so the ite is always the less oxygens, 8 is more oxygens. Okay, because that's 3 and 3, we don't have to do the charge crossing thing. If you did it, it would be 3 and 3, and you would reduce it down to 1 and 1. Okay, so I'm going to erase those. And it's just AlPO4. And then the last one, going from formula to name is a lot easier, isn't it? Calcium, nitrogen, but it changes to ide, nitride. Okay, so the only 2 we haven't done so far are the 2 type 2 metals. You're totally welcome to take a picture of this if you want to look at it later. Let me erase that stuff because that was not correct answers. Okay, so the last 2 are the 2 that are type 2, which is a little sad that I just had formula. Let's do one that's name first, name to formula. I'll just make it up. So let's say manganese to nitride. Okay, so manganese 2 means a 2+ charge. So Mn 2+. Nitrogen is a 3-, and then I cross the charges. Okay, so the formula there would be Mn3N2. Okay, for the other two that are formulas, we have to make sure to put the correct charge in parentheses. So the way that I like to tell you guys to do it is write down everything, leaving a blank for the charge, and then we'll figure out the charge. Okay, so chromium down here, chromium, some charge, and then PO4 is phosphate. Remember, I don't have to say how many there are of each of those. It doesn't matter that there's 3 and 2 in the name itself. It's only going to matter when I'm figuring out what the charge is. Okay? So chromium phosphate, and I need to figure out what charge the chromium is. So I do the reverse the charge thing. So I take these numbers and I crisscross them back up here. So the phosphate becomes a 3-, and the first thing I want to do is double check, does that match? Like, is phosphate supposed to be a 3-? I check my sheet. Yes, it is. Okay, that's good. That means that this chromium is correct. It is chromium 2. Okay, you have to do that check. We'll see why in a second. But you put the 3 up here, and then you say, is that right? Yes, that's right. Okay, so that 2 means that this is chromium 2. Not 2 of them, a charge of 2. Okay, the last one, tin, SN, tin something sulfate. Now, there's only one of each, right? So if I do the charge crossing thing, I should get tin 1 and sulfate with a -1 charge. But I have to ask myself, is that right? Does sulfate have a -1 charge? And I go to my exam equation sheet and I look up SO4 and I see that's not right. It's a 2- charge, okay? So the reason I do that check is because if the formula was like reduced down, then those won't match up, and it's a good reminder to you that you need to like scale them up. So by that, I mean write down what it actually is, SO4 2-, and say there were one of each of these, so what does the tin have to be? It has to match up with it, right? It has to be tin 2+. That was the only way that those actually matched. This is by far the hardest type of naming you could ever possibly have. A type 2 that when the formula was made with the charge crossing thing, it got reduced down. Okay, so this is the hardest you'll ever see. So this is actually tin 2 sulfate. And like I said, the best way to identify these is you do the cross the charge back up and you make sure it matches. And if it doesn't, then just write down what you know it actually is and then figure out what that has to be in order for them to balance. Would you have one of these on the test? Maybe, but only one for sure. Okay. I guess sometimes I like to do questions that are like, give you a pair. Like with naming, it's hard because I don't want to waste like a ton of questions on individual ones. So I might say like, here are sets of names and formulas. Tell me which one is incorrect. So there's like, pick 5 of these, right? And they're paired up with their name and their formula, and one of them doesn't match properly. So one of them could be like if I said tin 1 sulfate, that would be the incorrect one. Okay, if you want to take a picture, do it now, because I'm going to scroll away from it. So this is the end of naming. So you are completely ready to do the Chapter 3 naming dynamic study module. It's not due till Sunday night, but there's no good reason not to do it right now. So you have all the information. You can finish that one up. After today's class, the calculation side actually goes pretty fast. So we'll have one topic that we'll leave till Friday, but we'll finish up a lot of the calculation stuff. So if you've already done the naming thing and you're feeling pretty good about it, go ahead and move on to the calculation one, and you can do most of that one as well. And then last thing is that Chapter 4, we're starting on Friday. It'll be like mid-class. We'll get into it. So you'll have the Chapter 4 reading tomorrow. So I think we're starting to feel the pace of the semester. So we had an exam. Maybe it wasn't quite as good as you wanted. And you're like, okay, I really need to take this more seriously. Like, you need to take it more seriously today because it's picking up, not because it's like actually going faster, just because we're getting into material that built on the first unit. And so like if you're still struggling with the first unit, this is going to feel a lot harder. Okay? And it just keeps doing that. Sorry, that's how chemistry is. It just builds on itself. Okay. This stuff is actually really easy if you felt relatively comfortable with the calculations at the end of Chapter 2. Okay? If you didn't, now's the time to like get comfortable with the end of Chapter 2 calculations and do them in addition to what we're doing right now. Okay, so now we have to deal with masses of molecules and compounds, not just masses of individual elements. So if we had a problem that said like, what's the mass of 1 mole of oxygen, you would go to the periodic table and you would look up oxygen, and it's 16.00 grams per mole, okay? Now we need to be able to do the same thing, but for a compound. It's really not complicated. Something like water, H2O, you just go look up the hydrogen, you multiply it by 2 because there's 2 of them, you look up the oxygen, and there's 1 of them, you add them together. That's all it is, okay? If you want it for a single molecule, those numbers together would be AMU. If you want it for a mole, the number would be grams. And I don't show it up here, but AMU for 1 molecule, and I'm going to rewrite the moles down here, grams for 1 mole of water in this instance. And hopefully right when you saw me do that over and write something else, your brain's like, conversion factor. Okay, so if you have a list of conversion factor, here's another one to add. We're talking about masses, but now it's a mass of a compound, not just an individual atom. So I have them listed right here for water. You'll hear these called a few different things. Molar mass is probably like the mass of 1 mole. That's generic for atom or molecule, so you'll probably hear me use that term mostly. Your book likes to use the term formula mass because that's a generic term for covalent or ionic compounds. The other term is molecular mass or molecular weight, but that would only be specific to covalent compounds. So like it's just not as broad of a term. I'm going to say molar mass most of the time. Your book's going to say formula mass most of the time. Okay, so they are new conversion factors, either AMU for a molecule or grams for a mole. So I want you to take a minute and take a shot at this question. If you're struggling with this question, that's a good indicator that you're going to need to review some of the ideas from Chapter 2, because this should feel just like Chapter 2. It's just water now instead of an individual atom. Okay, so take a minute and then I'll start to work it up here. If you're lost, I'll give you, hints up here. And I'm going to go ahead and send around the roll as well. Okay, so there's your setup for the calculation. And then you just have to figure out where the numbers go. This one says 0.02. If you use our periodic table, it should be 0.016. I almost want to go find one from the end of chapter 2 to show you like how similar this is. I won't waste our time, but like this is just like if we said, oh, I have 11.56 grams of iron. How many moles of iron? Then I would go look up the molar mass of iron, 55.85 over 1 mole, and I'd figure out the number of moles of iron atoms. The difference here is that this is moles of water molecules. Okay, so picture a bunch of little water molecules now instead of a bunch of little iron atoms. Okay, it's no different. We're just counting the number of molecules now instead of counting the number of atoms. Any clarifications on this, or for that matter, how to calculate? You're going to practice it in a second, but how to calculate water's mass. So we go to the periodic table. There we go. Hydrogen's 1.008. There's 2 of them, so 1.008 times 2 plus the oxygen, which is 16. That's where we get the 18.016. Okay, we're going to do one that's a little bit more complicated in a second. Is that the next question? Yes, it is. Okay, so in this one, I use a messy, complicated formula weight for ammonium dichromate. Just remember that this 2 here means you actually have a total of 2 nitrogens and 8 hydrogens. So don't let that confuse you. When you've got parentheses and a subscript, it's like you have to carry that 2 in. So there's a total of 2 nitrogens, 8 hydrogens, 2 chromiums, and 7 oxygens in this thing. Okay, so we're going to determine the formula weight or the molar mass of ammonium dichromate, and then we're going to use that in a question. So feel free to continue on to the second part if you finish. Okay, so I've just written down the total number of each one, and now I'm going to go look up the masses. And then add all of those together. So double check your answer before you move on to the second part. Never, ever, 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 ever round these numbers when you're doing like a molar mass calculation. So you never want to worry about sig figs when you're doing numbers off the periodic table. You just use all the digits you have possible. Yep. Yes, yeah, times 2, times 8, exactly. So however many there are in the formula. The second part should look, again, very similar to something you would have seen at the end of chapter 2. It's just that now we're talking about moles of a big compound rather than moles of an individual atom. And we're just going to take that molar mass. Every time you see moles and grams together, you think periodic table. Okay? Moles and grams, immediately you want to think periodic table. So you've already done the calculation for this one, but like if you saw this question, 2.3 moles of ammonium dichromate, you know, what's the mass? You'd set up the calculation like this, and you'd say moles and grams, I need to go to the periodic table. Okay, so it's like you have this list of conversion factors in your head maybe, but more important than that is that you set up the calculation and figure out what conversion factor do I need, and then where do I get that information from. So if it's grams and moles, periodic table. Oh, and I guess this is 2 sig figs, so I'm going to leave this as 580. So you never want to round the molar mass itself just when you get to the end of a question like this. Okay, any clarifications about this? If you feel like you're like, oh, I didn't get this in chapter 2, you can look back in chapter 2 to clarify how to do these problems, but like just continue on with us and now do it for a compound, okay? So like you're just gonna learn it now instead of having learned it before. It's not like you have to go redo all of chapter 2. Okay. This one, let you guys kind of be a little bit independent on this one. And the second one is kind of new, but similar again to what we saw in chapter 2, just now for a molecule. Pretty sure my rain jacket is not going to be particularly insulating, but I'm freezing. Shove them in the back. So if you noticed, kind of had to know the formula there. Tetrachlorine, so 4 chlorines, 1 carbon. Okay, so on the first one, then we'll do the second part together if you haven't gotten there yet, that's fine. So in the first one, the blue is the setup, 8.73 moles. I'm looking for grams. So moles has to go on bottom, grams has to go on top. Anytime moles and grams are together, you go to the periodic table. In this instance, you go to the periodic table to find carbon and chlorine, and then add them up, multiplying the chlorine times 4, okay? So the overall molar mass of CCl4 is 153.81. That's how many grams are in 1 mole of that compound. Or another way of saying that is 6.022 times 10 to the 23rd molecules of CCl4 are going to weigh 153.81 grams. Okay, so then we just multiply it and get the overall mass in 3 sig figs. That's going to be 1,340 grams. So that's how much those lots and lots of molecules would weigh. We're going to figure out that number of molecules right now. So the last question says, how many molecules are contained in 8.73 moles of carbon tetrachloride? So when we set up the calculation, it's just, yeah, sorry, did I do something wrong?
I got 1,342.
Yes, but with 3 sig figs. So this is a good question. On the test, am I going to make you say that it's 1,004 or 1,342, whatever? No, I'm not going to have 42 and 40, but I might have 40 and I don't want you to be confused. Like, did she do it wrong? Did I do it wrong? Like, what happened? So I just put it in the correct number of sig figs, but you're right. It's 1,342.76, et cetera, et cetera. Yeah.
So in this we don't sig figs?
So I don't care about them in the respect that if you were doing a free response test, I wouldn't count it wrong. But on a multiple choice test, the correct answer would be listed as 1340, not as 1342, whatever. I won't put both of them though, because that would be testing you on the sig figs.
Why couldn't it be 1,342 versus 1,340? Why did you get rid of that 2?
Oh, because this one has 3 digits.
Okay.
So I want my answer to have 3 digits. And when I make this a 0, that now becomes not significant. Yeah, good clarification. Okay, so last thing, anytime you have molecules or atoms tied with moles, it's always Avogadro's number. So when I set up that thing and I had moles and something together, moles and accounting, it's Avogadro's number. Okay? All right, we'll pick up here on Friday, and then we'll also get into chapter 4 on Friday. See, and then I just put way too many sig figs. Okay. I do. Do you want to see which ones you got wrong?
I just want to see, make sure
I
it's
have a
accurate.
paper towel. I spilled my
Yes.
coffee.
No.
Never mind.
Never mind. Yes, it can.
Thank you.
Yep. Okay. Did you want to see what you got wrong?
I just want to see if it's accurate for
Yeah.
the most part, that's all.
Okay. What is your last name?
Shatkoff,
Like S-H...
18.
Brody?
Yeah.
Okay. I was like, is that your last name? Okay. That's that. And then here's the key, too. And then if you want to see the exam, I'm sure I don't, apparently. I don't have a blank copy, but I can pull it up on my iPad.